So, hello everyone again. This is lecture 1 part 2 of wave optics. In the last lecture we started with the concepts of introduction of wave optics. Let us move on with the further discussions in that only. I am Sameer Lavankar. Let us begin. So, the course outline is similar only. For now we are talking about the introduction part. Let us move on to the further discussions of introduction only. So, in the last lecture we started with the Descartes theory which analyzed as light as a corpuscular model of light. He proposed that the light is made up of tiny discrete particles called as corpuscles. Corpuscles is nothing but very tiny particles which travel in a straight line with a finite velocity and possess impetus. Then the laws of reflection and refraction were being also explained using this Descartes theory. But when a particular concept of this line was being analyzed using the refraction concept, that if the let us say a medium 1 passes a ray of light and that at an interface it bends towards the normal, according to the corpuscular model of light it was found that the velocity in the second medium is greater than the first medium. But on further experiments performed on the similar type of analysis, it was found that actually the velocity in second part is less than the first part. This explanation is further this explanation was being done by wave theory of light, or was being proved by wave theory of light. When the experiment on air and water using the ray of light was being performed, it was found that the velocity in the water is less than the velocity or the speed in air, confirming that the wave theory of light is intact, and hence the concept of refraction involving wave phenomena of light is also intact. So, this was we studied in the last lecture only. Then we also studied that Thomas Young performed several experiments, and finally when the wave phenomena of light was being proved, then the several more experiments were being performed such as interference and diffraction. So, today let us move on to the further discussions of introduction only. So, the only major difficulty was that since it was thought that the wave required a medium for its propagation, propagation as in movement, how could light waves propagate through vacuum? How could light waves propagate through vacuum? Because it was means when previous history wave plots were being formed, it was found that the wave always require a medium for its passage from point A to point B. But as it was already seen using experiments that light can pass through vacuum also. But if light can pass through vacuum, and if we try to propose or we try to prove this using wave theory of light, how can it be proved if wave cannot pass through a vacuum? So, this was only one of the difficulty, but it was also being explained. So, how it was explained? So, this was explained when Maxwell put forward his famous electromagnetic theory of light. Electromagnetic theory is nothing but the concept we learned in electromagnetic induction chapter. So, this was explained when Maxwell put forward his famous electromagnetic theory of light. Maxwell had developed a set of equations describing the laws of electricity and magnetism, and using these equations he derived what is known as the wave equation, from which he predicted the existence of electromagnetic waves. So, this was the explanation. Now, let us not go into further detail of what were the wave equations. Maybe these equations are in the different chapters. For now we got to know that the medium even without medium light can propagate, and hence wave theory of light is completely functional. So, from the wave equation Maxwell could calculate the speed of electromagnetic waves in a free space as in vacuum, and he found that the theoretical value was very close to the measured value of light. So, the theoretical value which he calculated using wave equation was found to be very similar, close to the actual speed of light. From this he concluded that light must be an electromagnetic wave. So, hence this difficulty was also being rejected, is also removed, and hence it is now completely clear that light is a wave phenomena. Thus, according to Maxwell, light waves are associated with changing electric and magnetic fields. So, this is just the basic concept of electromagnetic induction only, that if the magnetic field is being induced, then the current changes, or if the current is being changed, then the magnetic field changes. So, changing electric field produces a time and space varying magnetic field, and a changing magnetic field produces a time and space varying electric field, the basic concept of electromagnetic induction. So, the final concluding point of this slide is the changing electric and magnetic field result in the propagation of electromagnetic waves or light waves even in vacuum. So, the basic part of why it was being proposed using or resisted by Newton that the wave theory cannot be used for light as it cannot pass through vacuum, but using this Maxwell's explanation, Maxwell's equation, the Maxwell's derivation of equation of wave equation, it was finally proved that electromagnetic waves exist, and because electromagnetic waves or light waves exist in vacuum, hence light can be a wave phenomenon. So, this is the concept of this introduction part. Let us move on to a further slide away from the basic concept that does light travel in a straight line. This basic intact has been taken from your NCERT book only. So, just look over the discussion here, very firm discussion, very quick discussion. Please look over. So, in school you are shown an experiment in which you take 3 cardboards with pinholes in them, place a candle on one side and look from the other side. So, this is nothing but let me make if I can make a 3D diagram for this. Let this be those 3 cardboards, let these be the 3 pinholes talked about in the first line here. Then it has been shown that 3 cardboards with pinholes in them, place a candle on one side, let the candle be glowing here. Let the candle be glowing here and you are looking from the other side, that means your eye is being intact here. So, this is the direction of viewing. So, if the flame of the candle and the 3 pinholes are in a straight line. So, if this let me change the color. So, if this is in a straight line, if every pinhole complete model is in a straight line, then only we can see the, then only this person, this viewer can see the light, candle light. So, if the flame of the candle and the 3 pinholes are in a straight line, you can see the candle, quite evident. Even if one of them is displaced a little, you cannot see the candle. So, displaced as in, let me displace this only. So, this is the position, let me denote this position as B. If I displace it somewhat here, let this be position B dash, then this position of hole would be somewhat here. So, as this is not in a straight line, hence there will be no viewing of the candle. So, even if one of them is displaced a little, you cannot see the candle, quite evident. This proves that light travels in a straight line. So, as you can only view the light if it is coming in a straight line, hence it was proved that light travels in a straight line. So, this was an experimental analysis to prove how the what's the wave of what's the nature of path of what's the path of light's propagation. So, it was proved that light travels in a straight line using an experimental analysis, quite easy experimental data. Now, ray optics is based on, so ray optics was the first chapter you studied just before wave optics. So, ray optics is based on rectilinear propagation of light, rectilinear as in movement in a straight line. So, it is based on rectilinear propagation of light and deals with mirrors, lenses, reflection, refraction, etc. These are all the concepts we talked in the last lecture only, sorry, last chapter, you may have studied it. So, it was ray optics. Then you come to this chapter on wave optics. So, now you are told that light travels as a wave, that it can bend around objects, it can diffract and interfere. So, when we studied the concepts of ray optics, we talked about convex lenses, concave lenses, refraction, reflection concepts, laws of reflection, laws of refraction, etc. But when we get to know about waves, in the subsequent lectures you will get to know, we will get to know the concepts of wave front, then Huygens principle, interference, diffraction. So, the properties are also being different, properties depicted are also different. Then why are we, how to prove similarities between the same, how to prove the basic essence of light, that because to understand that concept only I took this part also out of NCERT book. So, just to iterate to you again, so ray optics is based on rectilinear propagation of light, in which we dealt the concepts of refraction, reflection, then lenses, mirrors, etc. In wave optics we will get to know about wave nature. So, in wave nature what does wave do is it can also bend around objects, bend as in, let us say if this is the if this is the object, let us suppose, then it can even bend around it, and move in this position, move in this direction also. This is known as bending around the object. So, it can diffract and interfere. What is diffraction, what is interference, we will get to know in subsequent slides. For now, let us move to the next slide, what it is talking about. So, in optical region, light has a wavelength of about half a micrometer. Half a micrometer as in 0.5 mu m. If I write it in terms of meters, it is 0.5 into 10 to the power minus 6 meters. So, in optical region, light has a wavelength of about half a micrometer, very small when we compare it with the dimensions of actual data. Let us say this pen also, or let us say this screen, anything has a very large dimension when it is compared with the wavelength of light. So, the light has a wavelength of about half a micrometer. If it encounters an obstacle of about this size as in if the specimen or the sample is also of around this only, let us say it is of 1 to 2 micrometers. This is the obstacle, let me write it like this. If this is the obstacle, then it can bend around it and it can be seen on the other side. So, it can bend around it as in, let us say, so to explain this line, what does this line says, what does this line says, ki let us say I am viewing any object from this position. If these are the 3 holes and this is the, if this is the obstacle, then if this is let us say 1 to 2 micrometers of size, and as we know that the light has a wavelength of half micrometers, then what does it say is, if I even change the position, if I even displace it a little, because the wavelength or because the dimension is approximately same with the wavelength, it can even bend around it. Bend around as in the light can bend like this, light can even bend and go towards our eye, and hence then also we can see that particle. So, this is the concept we talked about in the second point, that if it encounters an obstacle of about this size, it can bend around it and it can be seen on the other side as in viewer. Thus, a micrometer size obstacle will not be able to stop a light ray. Thus, so if the obstacle here, let us say this is the obstacle being talked about here. So, if the obstacle is of let us say 1 to 2 micrometers being intact in this point, then it can so how it can bend around it, let us say this is the obstacle, let me write it like this. So, how does it pass through it is, it goes like this, it bends like this. Let me change the color for more clarity, let this be the obstacle, let this be the light coming. So, when it approaches this, it bends like this and then it again goes. So, this is known as bending upon hitting up the obstacle. So, if the wavelength of the light is 0.5 micrometers, if the wavelength and the obstacle are of similar dimensions or similar what we can say similar length, then only this bending can occur. And so, if let us say this is the concept being talked about here is, let us say this, if this is the eye, these are the pinholes and this is the obstacle being here. Let us say let me make a zoomed in portion of this portion here. So, what I am saying is, let us say the obstacle is being kept here and this obstacle is of 1 to 2 micrometers, and if I want to see the candle light up here, then this light can also be seen. So, when the light approaches here, if I see the zoomed in portion, then let me change the color. So, zoomed in portion will have a light bending around this obstacle like this and then directly reaching to the means the light from candle will reach towards our eye. So, the movement will be like this. So, this is the only concept we talked about if we need to propagate using the wave theory, or we need to understand this concept using wave theory of light. So, moving on. So, thus a micrometer size obstacle will not be able to stop a light ray if the obstacle is much larger. So, if this is much larger, however, light will not be able to bend to that extent and we will not be able to see to the other side. So, if this is not say let us say this is 1 to 2 centimeters only. So, this will not be able to bend around it and hence we cannot see the light. So, this is a property of a wave in general and can be seen in sound waves too. So, this concept is not only limited to light waves, this can also be similar to sound waves. So, how can we let me make an example of sound wave also. Let us say I need to speak and there is a portion which is hearing from let us say 5 centimeter 10 centimeters away. I make a sound resisting boxes and I only open a small hole. Let us say my passage of sound which is propagating from my mouth to the ears of the other person which is hearing this is only through that small hole. If the obstacle is very small, let us say 1 to 2 micrometers, it will not make any difference. The sound waves propagating from my mouth will directly hit that obstacle, bend around it, and will and the person hearing it can directly hear it. But if the obstacle is very large, it can't bend around it, and hence the person cannot hear it, and hence the hence my sound wave stops at that cardboard or at that location, at the registering point. So, this similar light wave concept can also be analyzed, or can be also explained using an example of sound waves also. So, this was the complete concept being talked about in the first 4 points. Moving on, so the sound wave of our speech has a wavelength of about 50 centimeter to 1 meter. So, wavelength differs for a light and sound waves. So, the sound waves of our speech has a wavelength of about 50 centimeter to 1 meter. If it meets an obstacle of the size of a few meters, it bends around it and reaches point behind the obstacle, as being talked about in the similar analogy of light waves. But when it comes across a larger obstacle of few hundred meters, such as the hillock as in the hills, hilly regions, or what we can say mountains, most of it is reflected and it is heard as an echo. So, you know the concept of echo, which you have maybe learnt in previous lectures or previous chapters. So, echo is nothing but the reflection of the sound waves. So, just the same analogy of light waves were being analyzed using the sound waves here. So, let us move on to the last concluding point of this concept. So, hence in cardboard experiment, when we move any cardboard, the displacement is of the order of a few millimeters. So, displacement being talked about in this is of few millimeters. So, this displacement is nothing but a few millimeters. The displacement is which is much larger than the wavelength of the light. So, quite evident, as millimeters is nothing but 10 to the power minus 3 meters, but micrometer, let us say 1, this is 10 to the power minus 6 meters. So, quite evident that the amount of deflection is 10 to the power 3 times or 1000 times more than the wavelength of wavelength of the light, because so hence the obstacle is very large, it cannot bend around it, hence the light is not visible, the candle light is not visible to our eyes. So, hence in cardboard experiment, when we move any cardboard, the displacement is of the order of a few millimeters, which is much larger than the wavelength of light, hence the candle cannot be seen. If you are able to move one of the cardboard by a micrometer or less as in 0.5 micrometers or 0.3 micrometers. So, that will be in the dimension similar to the wavelength of light, then the light can bend around the obstacle. The obstacle here can be the periphery of the pinhole we are talking about. So, then if you are able to move one of the cardboard by a micrometer or less, light can be able to diffract. What is diffraction we will get to know in subsequent slides. For now, if you are able to move one of the cardboard by a micrometer or less, light will be able to diffract and the candle will still be seen. So, if it is possible to displace the cardboard by, let us say, 0.5 into 10 to the power minus 6 meters, then it can be visible. That it can be visible as in the complete propagation can also be visible then, but this time light will not be travelling in a straight line, light will be has a smaller band which may be not even visible to the naked eye. So, this was the complete concepts of introduction and the small portion of does light travel in a straight line. Let me conclude here only, I will not start the next principle right now because it will take time. Just to conclude the complete introduction part, and this part is, let me start from the first slide only. So, in 1637 what Descartes do, he did a corpuscular model of light. Corpuscular model, as the name suggests, is very tiny particle. So, he understood or he explained the concept of light moving in a group of particles. So, group of particles is being similarly explained here in the right side also. So, using these experiments of using this as light as a particle theory of light, he explained the laws of reflection and refraction. But one of the theory which he included in this was that on refraction of a medium 1 to medium 2, if the light bends towards the normal, the velocity in the second medium is greater than the first medium, which is not in proportional, which is not even intact with the real life scenario. Hence, wave theory of light came into picture. So, majority of the wave theory experiments or being work done was being intact and was being able to prove, but only problem was that when we tried to explain the wave theory, it was not being proved because the vacuum, the light also travels through vacuum, and wave theory of light cannot be explained through vacuum part. But when further analysis was done, when further research was being done by the prominent scientist Maxwell, he explained the complete concept using electromagnetic theory of light, and finally using the wave equation we got to know, when he tried to find out the velocity of light in vacuum using wave equation, it got to be almost similar, or it got to be almost accurate as the actual measured value of speed of light. So, hence this vacuum concept was also being removed, and finally wave theory of propagation or wave theory came into existence. Finally, we got to know a smaller concept of light travelling in a straight line. So, the bending up of light on an obstacle coming into its path, if the dimensions of that path is in accordance with the wavelength, was being told in this concept here. Moreover, we also got to know about the analogy between the light wave and the sound wave. Just the difference is that the sound wave has a larger wavelength of the order of 50 centimeter to 1 meter. So, the dimensions also should be in the dimensions of 50 centimeter to 1 meter. If the dimensions are very large, let us say in 1000 meters, or let us say in 100 meters, few hundred meters, then the bending up of sound waves cannot occur, and hence echo is formed. So, this was the complete concept about introduction and the light travelling in a straight line. So, it is quite clear that light does not travel in a straight line. It may travel in a straight line if the obstacle is not present, but if an obstacle of the similar wavelength, similar dimension of the wavelength of light is present, then it will bend around it. So, this was the complete concept. From the next lecture, we will start with the Huygens principle. What is Huygens principle? A little bit about Huygens I will also explain to you what are the prominent works he did in his entire life. For now, let us stop it here only. So, thank you.